If math has been driving you crazy, or if you're finally admitting you're lazy, and your test grades have been dropping, it's time to get your arrows popping.
Ladies and gentlemen, this is Mr. Whitt with Fort Bend Tutoring, and today's tutorial is going to be about graphing rational functions with slant asymptotes. That's right, oblique asymptotes, some would say. That's what I'm bringing you today. Oh, he is rhyming. Thank you. Thank you. Applause. Applause. But let's continue. But first, go ahead and subscribe by clicking on that subscribe button and also clicking on the bell icon so that you can know when we are uploading new and fresh content for you to view and watch and like. Speaking of which, go ahead and click that like button because every like counts. There you go. Well, let's go ahead and move forward with a snapshot of what I have for you today, ladies and gentlemen. That's right. We have 4 problems here that we'll be graphing and answering many of the questions that you may find in your college algebra class, in your algebra 1 class, in your algebra 2 class, as well as your pre-calculus and calculus classes. So let us dig in to the following. That's right. So to recap on our foundations from part 1 and part 2 of this 5-part series, a rational function is when you have a function in the form of p of x divided by q of x, where p of x and q of x are both functions and q of x does not equal 0. Why? Because you can't have 0 in the denominator of a fraction because it makes it undefined. That is correct. You must avoid that at all costs. That's right. So here we have our parent function, f of x equals to 1 divided by x, and you see the form of the basic parent function there for a rational function. And these are the steps to graphing a rational function. Number 1, go ahead and factor completely. Number 2, you want to identify any holes that you may have. Find your vertical asymptotes. Find any horizontal asymptotes that you may have. Find your oblique/slant asymptotes, as what we'll be doing in this video. Find your domain. Find any intercepts and points that you may have on the horizontal asymptote or oblique asymptote. And for number 8, you'll be graphing your asymptotes and intercepts. And for number 9, we'll be making an XY chart and graphing the function. Finding the range is number 10. And finally, because of your great interaction, we have added for you the end behavior of the rational function. Oh, yes. So we'll be doing quite a bit with each and every problem we have in this video. So here we have problem number 1, where we have f of x equals to x squared divided by 2x plus 1. Let us begin by identifying that vertical asymptote by setting the denominator equal to 0 and solving for it. So I have 2x plus 1 equals 0, and solving for x, I'll be subtracting 1 to both sides of the equation. We have 2x equals -1, and then dividing both sides by 2, we'll end up with the vertical asymptote x equals -1/2. This is our vertical asymptote, and of course, it's going in a red box. Thank you, because that's where we place our solutions. Red box in it. That's right. On to identifying the oblique/slant asymptote. Because the degree of the numerator is 1 more than that of the denominator, in other words, our numerator's degree is 2 because our variable's exponent is to the 2nd power, and the degree of the denominator is 1 because our term 2x has the variable x to the 1st power. So what you want to recognize is that these exponents on the variable x have a difference of 1. Anytime they have a difference of 1 when you're dealing with a rational function, you will most likely end up with a slant asymptote. So our next step is going to be to use long division to divide the numerator by the denominator. So I'll have 2x plus 1 going into x squared, and you can show any missing terms that you may have by putting in these placeholders like so. From here, what do I need to multiply 2x by in order to get x squared? Well, I would need to multiply by 1/2 x. Then multiplying 1/2 x times 2x plus 1, you'll distribute to get 1/2 times x times 2x to give you x squared, and then 1/2 x times 1 gives us 1/2 x. From this point, change the signs. That's right. And if you need a refresher over how to use long division when dividing polynomials, go ahead and check out this video, which I'll put a link right here for you, okay? For dividing polynomials, it's really informative. Go ahead and check that out and like it. Thanks. So from this point, we're going to be able to bring down a negative 1/2 x plus 0. Now we want to see what we need to multiply 2x by in order to get negative 1/2. Well, in this case, we'll need to multiply by negative 1/4. So multiplying negative 1/4 times 2x, you'll end up with negative 1/2 x. And multiplying negative 1/4 times 1, you'll end up with negative 1/4. From here, we will change the signs. So we'll be bringing down 1/4. And since we can't multiply 2x by anything to get 1/4, we'll say that that is the remainder. And what's most important to remember is that it is this quotient, not including the remainder, that will become your slant asymptote. So therefore, our slant asymptote is y equals 1/2 x minus 1/4. And here is the slant asymptote. Red box it. Red boxing it. There you have it, guys. So we now know what our slant asymptote is. So let's go ahead and move on. The next thing you want to identify is the domain. Once again, you cannot have 0 in the denominator of a fraction, so therefore we'll set the denominator 2x plus 1 not equal to 0 to help us identify the domain. So we'll be subtracting 1 to both sides of the equation. You'll end up with 2x cannot equal to negative 1. Then by dividing both sides by 2, we'll have x cannot equal negative 1/2. And of course, we'll probably have to write this in interval notation. So because we're excluding negative 1/2, our interval notation for the domain will be negative infinity to negative 1/2 union negative 1/2 to positive infinity. All right. So that is our domain. Red box it. All right. That takes care of the domain. And now for our x-intercept, you're simply going to set the numerator equal to 0 and solve for it. So our numerator is x squared. You'll set that equal to 0. You can then take the square root of both sides of the equation and find out that x equals 0. Therefore, as an ordered pair, our x-intercept is 0, 0. That's it. Red box it. Red boxing it. For the y-intercept, what you'll want to do is you'll want to plug in 0 for x and solve for y. So in other words, you want to find out what f of 0 is. So plugging in 0 for all the x's and then simplifying, we'll have 0 squared divided by 2 times 0 plus 1. This equals 0 divided by 0 plus 1. From here, we'll have 0 divided by 1 for a result of 0 for the y-intercept. So as an ordered pair, you'll have, once again, 0, 0, the origin. Of course, who didn't see that coming? So let's go ahead and red box that. Red boxing it. All right, let's continue. Now we have our original function, f of x equals to x squared divided by 2x plus 1, and we have our slant asymptote of y equals 1/2 x minus 1/4. So now what we're going to do is we're going to keep in mind that at negative 1/2, our function is going to be undefined because of the vertical asymptote, especially since we can't have 0 in the denominator of this function. So I'll be utilizing the fact that at x equals to negative 1/2, our function is undefined to determine what other x values I can use to generate our xy chart here. So what I'll do is I'll move incrementally to the left and right of negative 1/2. And by the way, I'm a little lazy, so I like to use integers instead of fractions. So I'll be moving to negative 1, negative 2, and negative 3 here, as well as 0, 1, 2. From time to time, some of your y values may be improper fractions, so since we're actually graphing this function, you might find it beneficial to go ahead and change those into mixed numbers as I do, because for me it's easier to locate these points on the Cartesian plane if I'm dealing with integers and mixed numbers. All right, so that being the case, let's go ahead and begin by graphing our vertical asymptote. So I'll have a dashed vertical line representing our vertical asymptote, x equals negative 1/2. All right, just like that. Then moving on to our slant asymptote, the oblique asymptote is y equals 1/2 x minus 1/4. We'll start by having a y-intercept at negative 1/4 first. We'll put a point there, and then we'll go up 1 and over 2, representing this slant asymptote here. And so you can also go down and to the left 2, down and to the left 2. All right, just like that. And so let us come up with our representation of the oblique asymptote, just like that. All right, so now that we have all of this in play, okay, then what you'll want to do is you'll want to go ahead and plot your points on your rectangular coordinate system here. So let us begin with the easy ones, right? So like at -1, -1. And because our slant asymptote is so close to the actual points, you'll want to verify whether or not your points belong above or below the slant asymptote. So for instance, I know I have a point at the origin, right? Okay, I know I have a point there. But if I were to plug in 0 into our slant asymptote, I would find out that result would be -1/4. So this shows me that the line should be beneath the point 0, 0. Okay, and it is. So it's just a matter of verifying whether you're on the correct side of the slant asymptote. Whereas at the point -1, -1, I can confirm that if I were to plug in -1 into the slant asymptote, I would end up with -3/4 as a result. Well, -3/4 is higher on the graph than -1 is. So that means that the point -1, -1 should fall beneath our slant asymptote. All right, so that's really important to verify, especially if your points that you're generating are close to the slant asymptote. You want to make sure that you're plotting your points in the correct area. So now we can plot our other points, such as 1 1/3. So 1 1/3 will be right there, and then we have 2 4/5. So we'll have a point about right there on the right side of the vertical asymptote. So next, let's plot -2 and -1/3. Notice that your points are going to be really, really close to your slant asymptote. So what you can continue to do is to verify whether or not you're plotting the points on the correct side of the slant asymptote. So if you need to do that, just remember to plug in your same x value into your slant asymptote to confirm that you're plotting the point on the correct side of the line. For instance, plugging in -2 into the slant asymptote, you'll end up with -1 1/4, and -1 1/4 is a higher y value than -1 1/3. Therefore, I am confirming that my next point should be on this side of the line here. Okay, so based on our asymptotes, our parent function, and what we already see here, I know that this graph will look just like this. That's right, in all of its glory. Okay, and here we have our graph with our slant asymptote. So notice how close our points are to the slant asymptote. Once again, if you need to verify that you're plotting your points on the correct side of that slant asymptote, do not hesitate to verify that by plotting in the same x value into the slant asymptote and do your comparison from there. Now let's look at our range. Notice how our graph has a peak right here in this area and a valley right here in this area. Well, due to that, there's going to be quite a few values in between there that our range cannot be. In order to accurately identify these values, you can use either a calculator or you can use techniques in calculus that unfortunately I will not be covering with you in this particular video. So instead, we'll use our TI Inspire CX-Cast software to identify where this stops off and where it picks back up for our y values. All right, well, using our TI Inspire Cast, what we'll do is we'll go to menu, and then within the menu you're going to go to analyze graph, and let's first of all find out where this is going to stop as we move up from -infinity. That particular point occurs. All right, so that highest value actually occurs at -1, -1, and we had that on our graph. Then what you'll want to do in order to find out the point where it picks back up, you'll go to menu, then go to analyze graph, you'll go to minimum, and then you'll set up your lower bound and higher bound here, and we find that we have a minimum value of 0, 0. So values between -1 and 0 will not be available for this function here. They'll be excluded from the range. So we'll write that as -infinity to -1 union 0 to +infinity. So this is how you can use your calculator to help find the values that are being excluded from the range. So now that we've identified that, and once again we have our range from -infinity to -1 union 0 to +infinity. Now as far as our end behavior is concerned, as x approaches -infinity, y approaches -infinity, and as x approaches +infinity, y approaches +infinity. So there we have it for problem number 1. Done and done. Red box it. That's what we're going to do. And we got a box around our end behavior, a box around our range, and of course we have our graph. There you go. All right, so let's move on to problem number 2. For problem number 2, we have f of x equals x squared plus 2x divided by 3x minus 1. So the first thing you'll want to do is write this out in its factored form. In the numerator, we can factor out an x, so that leaves me with x times x plus 2. Then in the denominator, we can factor out nothing. So just bring down that 3x minus 1. Okay, so here is our factored form of our original equation. Well, it doesn't tell me much other than the fact that we won't have any holes in this graph. All right, so that's something good to know. Also, it lets me know that I'll most likely have two x-intercepts when I set this numerator equal to 0 and solve for it. As far as our vertical asymptote is concerned, you'll be setting the denominator equal to 0 and solving for it. So you'll have 3x minus 1 equals 0, and then by adding 1 to both sides of the equation, we'll end up with 3x equals to 1, and then by dividing both sides by 3, we'll have x equals to 1/3 as our vertical asymptote. Just like that. Then, as far as our oblique asymptote is concerned, because our degree of the numerator is 1 more than the degree of the denominator, we'll be using long division in order to identify this. So I have 3x minus 1 going into x squared plus 2x plus 0, showing all of my missing terms in that expression. 3x would have to be multiplied by 1/3 x in order to get x squared as that first term in our dividend here. So 1/3 x times 3x gives you x squared, and then 1/3 x times -1 gives me -1/3 x. From here, you want to change the signs, just like that. Then combining the 2x and the 1/3, you'll end up with 7/3 x plus 0. So what we would need to multiply 3x by in order to get 7/3 is going to be 7/9. So multiplying 7/9 times 3x gives you 7/3 x. Multiplying 7/9 times -1 gives you -7/9. And of course, changing the signs, and the 7/3 x's will cancel out, and you'll end up with the remainder. Once again, we don't really care about the remainder. Now, when it comes to the slant asymptote, all we care about is this quotient up here. Therefore, our slant asymptote for this equation is going to be y equals 1/3 x plus 7/9. And this is our slant asymptote for problem number 2. Red boxing it. So we have our oblique asymptote. We also have our vertical asymptote. There we go. As well as our factor form. Let's not be disrespectful here. Okay. For our domain, we can't have 0 in the denominator. So therefore, after setting this 3x minus 1 not equal to 0 and solving for it, by adding 1 to both sides, and then by dividing both sides by 3, we'll find that x cannot equal to 1/3. Therefore, in interval notation, we'll have -infinity to 1/3 union 1/3 to positive infinity. And there is our domain for this function. For our x-intercept, you'll be setting those factors that I told you about equal to 0. Remember, we factor that numerator into x times x plus 2? Go ahead and set those equal to 0. So x equals to 0. That's already done. So therefore, you'll have an x-intercept at 0, 0. And then the other one was x plus 2 equal to 0, right? So if you subtract 2 to both sides, you'll end up with x equals to -2. Therefore, -2, 0 is another x-intercept that we have. For our y-intercept, you would simply be plugging in 0 for x and simplifying, which would give you 0 over -1. So that just confirms that origin thing again that we just had, right? Red box it. We have a y-intercept at 0, 0, 2 x-intercepts, like so. And the domain. Yeah, let's not forget the domain. There we go. Red boxing it. So let's not forget that our slant asymptote is y equals 1/3 x plus 7/9. So we'll put that right there. And of course, we have a vertical asymptote of x equals to 1/3. Okay. So knowing that we're going to be positioned around 1/3, in other words, that 1/3 is where this function will be undefined, let's find values on either side of this. So let's go to, for instance, 0. 0 is a good friend. In fact, we know that that's one of the intercepts that we'll be dealing with this problem. And let's also move on to -1 and -2. Then to the right of 1/3, let's use values like 1, 2, and 3. Okay, looks good to me. So don't forget that we also had an x-intercept of -2, so we know that value already. Let's go ahead and find out the rest of these y values for the values that I chose. So we're going to end up plugging in -1 into the numerator, so that'll give me 1 minus 2 is going to give me -1 in the numerator. All right, in the denominator, 3 times -1 is -3 minus 1 gives you -4. So this value is positive 1/4. All right, there we have it. Continuing on, we'll be plugging in 1. And so plugging in 1 in the numerator, you'll have 1 plus 2 gives me 3 over 2. Plugging in 2, you'll have 2 squared is 4. 4 plus 4 gives me 8 in the numerator over 3 times 2 is 6, and then 6 minus 1 is 5. All right, so as a mixed number, this will be 1 3/5. Once again, I love using mixed numbers when it comes time to graph because, yeah, it's easier. Thank you. Plugging in 3, we'll have 9 plus 6 is 15 in the numerator. Then in the denominator, you'll have 9 minus 1 gives you 8. So as a mixed number, this will be 1 7/8. Okay. So let's begin by graphing the asymptotes. We know we have an asymptote of x equals 1/3. Let's go ahead and graph that. So 1/3 is pretty close to 0. So I end up with a dashed line right here to the right of the y-axis. Then I have my oblique asymptote. So I start at almost 1 on the y-axis, and this will represent that y-intercept of 7/9 in the slant asymptote. So I'm going to go up 1 and then to the right 3. So I have a point here. Then I'll continue to go up 1 and then to the right 3. I can also go down 1 and then to the left 3, down 1 and then to the left 3. And here I have points that are going to be on my slant asymptote. So let's go ahead and represent this with a dashed line, just like that. Okay, there you go. Let's go ahead and plot some points, shall we? I think I'm going to start by plotting our intercepts. We have a point at 0, 0. All right, there we go right there. Then we also have a point at -2, 0. So that's right here. Notice that once again, it's really close to our slant asymptote, but we have already proved that we're going to be beneath the slant asymptote at this point. If you're ever curious about whether or not a point is actually lying on the slant asymptote in this case, simply plug in that same x value into the slant asymptote and see if it gives you the same y result. All right. In this case, plugging in -2 does not generate 0. So we're good. So now we also have this point at -1 1/4. So that gives me a point here. And then to the right of the vertical asymptote, we have a point at 1 and 1 1/2. All right. So that means that I have a point at 1 and 1 1/2. It's going to be right here. Okay. Continuing on, we have a point at 2 and 1 3/5. 2 and 1 3/5 is going to be about right here. And then we have a point at 3 and 1 7/8. All right. So we got it right there. So this means that our graph is going to look like this, guys. Just like that. And on the right side of the vertical asymptote will be looking just like that. And this is going to be the graph of our rational function. So as far as our range is concerned, using our TI Inspire CX cast to identify where this maximum value is and this minimum value is so that we can accurately write our range, you're going to go to menu, and then analyze graph, and then let's go to maximum. And so we'll set an area to start looking for the maximum here, and notice that it picks it up to tell us that our maximum value here is approximately 301 thousandths on the left side of our vertical asymptote. Then on the right side of our asymptote, we're going to be identifying this minimum value here to find out where it picks up again. So we'll go to menu, analyze graph, and go to minimum. And then we'll start about here and move over here, and it's identified the minimum value. So let's move that right up there. Okay. So based on that, our range is going to be from -infinity to approximately 301 thousandths, union approximately 1 48/100ths to positive infinity. So this will help us accurately identify our range when we have slant asymptotes. There are ways to do this by hand using calculus. However, I won't be covering that in this particular video. So our end behavior, well, as x approaches -infinity, y also approaches -infinity. And of course, just love on the negative infinities because I know they're ugly. Okay? But somebody's got to be. And then you're going to have as x approaches positive infinity. Oh my! See, okay, I will fix that one because that was hideous. Then y will also approach positive infinity as well. There we go. So this is going to give us all that we need for this particular function. Red box it. Red boxing it. That's right. That's what we're doing here. Red boxing our answers. And as you see here, we have graphed our function correctly. Moving on. In problem number 3, we have g of x equals x squared plus 2x minus 3 divided by x plus 1. So if we look at our factored form of the problem, we could rewrite g of x as x plus 3 times x minus 1 divided by x plus 1. So this shows us that yes, the numerator can be factored, and thus we'll end up with more than one x-intercept, but also that we don't have any holes, as none of the factors will cancel out with the denominator's x plus 1. So we'll move on now to the vertical asymptote. In that vertical asymptote, you're going to set the denominator equal to 0. You'll have x plus 1 equal to 0, and then solving for this, after subtracting 1 on both sides, you'll have x equals to negative 1, and there you have it. The vertical asymptote. All right. For the slant asymptote, the oblique asymptote, you're going to divide the numerator by the denominator. So using long division, I'll set this up as x plus 1 going into x squared plus 2x minus 3. The x need to be multiplied by x, and x times x gives us x squared. X times 1 is x, and then we will change the signs. This gives us now x minus 3, and I need to multiply x times 1 in order to get x. So if I distribute, you'll have 1 times x is x. 1 times 1 is 1, and then you will change the signs. This gives you a remainder of negative 4, but what we want is this quotient right here, the x plus 1. Therefore, our result for the slant asymptote is y equals x plus 1. Red box it. There you go. Red box for you. Red box for the vertical asymptote. And a red box for the factored form. There we go. Lovely. From here, we'll go ahead and identify the domain. Remember, we cannot have 0 in the denominator of this rational function. Therefore, by setting the denominator not equal to 0, we can identify the values that x cannot be, and in turn, that'll help us find what x can be. So we know that x cannot equal to negative 1. So for our domain, we'll write that as negative infinity to negative 1 union negative 1 to positive infinity, and this is our domain. Yeah. For the x-intercept, you'll take both factors that we found in the numerator and set them separately equal to 0 and solve for it. Remember that we factored the numerator into x plus 3 times x minus 1. Both factors will be set equal to 0 separately, and then you'll solve for it. So you'll find that x equals to negative 3 and that x equals to 1. Well, with that information, we know that the ordered pairs will be negative 3, 0 and also 1, 0, just like that. All right, those are our x-intercepts, guys. For the y-intercept, you can simply plug in 0 for all the x's and simplify. That'll give us negative 3 over 1, which is negative 3. So our y-intercept is going to be at 0, negative 3. And in order to find out that y-intercept, you want to find out what f of 0 is. So we had 0 squared plus 2 times 0 minus 3 divided by 0 plus 1. And that gave us negative 3 over 1, which is negative 3. All right, so that's how we ended up with that y-intercept. Yeah, just like that. Red box it. Got a box around my y-intercept, the two x-intercepts that we have here. Yep, as well as the domain. Done and done. All right, let's move along. So we know that we have a slant asymptote of y equals x plus 1. We sure do. And also we have a vertical asymptote of x equals to negative 1. Yep. So when x is negative 1, the function is undefined. And we'll be choosing values to the left of negative 1, like negative 2, negative 3. Okay, let's go with negative 4. All right, I'm not scared. And then we also have 0, 1, and 2. From here, let's go ahead and graph our asymptotes. So at x equals negative 1, we'll have a dashed line here at negative 1. X equals negative 1, vertical line right there. And then I have a y-intercept of 1 for the slant asymptote, which is y equals x plus 1, by the way. You're going to go up 1 and over 1, up 1 over 1. We can go down 1 into left 1, down 1 into left 1, down 1 into left 1. Okay. And then we'll have a dashed line right right through there. There you go. There you go. There's your slant asymptote. Just like that. Now, let's go ahead and find out the rest of these values on the XY chart here. We know that we have intercepts at 0, -3. We know that. We know that we also have it at -3, 0. And we have it at 1, 0. Okay. Plugging in our other values, we'll have -4 plugging into the function. We'll have 16 minus 8 is 8. 8 minus 3 is 5. And then that'll be 5 over -4 plus 1 is -3. And we'll rewrite that as -1 2/3. Plugging in -2, you'll have 4 minus 4 is 0. That's -3 in the numerator over -1. That gives you a result of 3. Then plugging in +2, you'll have 4 plus 4. That gives you 8 minus 3 is 5. And in the denominator, you'll have 2 plus 1 is 3. So this also becomes 1 2/3, but a positive version. Okay, let's go ahead and plot our points here. And I believe I'll begin with the intercepts. So we have a point at -3, 0. All right. We also have a point at 0, -3, which would be here. Okay. And we have a point at 1, 0, which is here. Yeah. Okay. And from there, we have a point at -4 and -1 2/3. Be about right there. And then we have a point also at -2, 3. So -2 and that's 3 here. And then we also have a point at 2 and 1 2/3. 2 and 1 2/3 is here. All right. Well, ladies and gentlemen, that means that my graph is going to be doing this. Just like that. Also, right here, there you go, there you go, there you go. That's cute. There's your graph. There is your graph. And lo and behold, it looks like we don't need any help identifying the range in this case, because our range will be from -infinity to +infinity as we have no gaps. We have no gaps as far as our y-axis is concerned. Nothing is stopping us here from going from -infinity to +infinity. Therefore, your range, -infinity, +infinity. As far as our end behavior is concerned, as x approaches -infinity, y approaches -infinity. And as x approaches +infinity, y approaches +infinity. There you go. This completes problem number 3. Red box it. That's right. Go ahead and put a red box around there. Be proud of your work. Show off for your teacher. Don't make it hard for them to find your answer. Thank you very much. Yeah, there you go. That was good stuff right there. All right, so let's go ahead and check out problem number 4. For problem number 4, we have f of x equals 2x squared minus 5x minus 2 divided by x minus 2. This function cannot be factored, therefore we don't have a factored form of the function. So instead, we'll begin by looking for the vertical asymptote. And that means that we'll just be setting the denominator equal to 0. So we have x minus 2 equals 0, and then solving for x by adding 2 to both sides, you'll have x equals 2, and this is the vertical asymptote. I'm going to go ahead and put a red box around this. There you go. For the oblique asymptote, we'll need to do the long division. So dividing the numerator by the denominator here, knowing that the degree of the numerator is 1 more than the degree of the denominator, I'll have x minus 2 going into 2x squared minus 5x minus 2. X goes into 2x squared, 2x times. 2x times x is 2x squared. 2x times -2 is -4x. And then I will change the signs here. So this gives me now a -x minus 2. We can multiply x by -1. And -1 times x is -x. And -1 times -2 is +2. And then you will change the signs to end up with a remainder of -4, by the way. So with this remainder, that lets me know that I'm done, because all I need is this right here. That's right. The slant asymptote is going to be y equals 2x minus 1. Red box it. Red boxing it. Just like that. Yeah. And now, continuing on, our domain will be excluding the number 2. Yeah, we'll exclude that. So you can just go ahead and write your domain as -infinity to 2. Union 2 to +infinity. And there you have it. Red box it. Red boxing it. Thanks. Your x-intercepts, well, you can use the quadratic equation to identify those, perhaps, since this is not factorable. So let's say that your value of a equals to 2, b equals to -5, and c equals to -2, and we plug it into the quadratic formula, which is negative b plus or minus the square root of b squared minus 4ac all over 2a. You'll end up with the opposite of -5, plus or minus the square root of -5 squared, minus 4 times 2 times -2. All over 2 times 2. This gives you 5 plus or minus the square root of 25 plus 16. All over 4. This equals 5 plus or minus the square root of 41 divided by 4. Yeah, and as ordered pairs, you could say that this would be 5 plus or minus the square root of 41 over 4, 0. So you'll have two of them, one with the minus sign, one with the plus sign. And of course, you can get decimal notation for this with a calculator. Thanks. But these are the exact x-intercepts for this particular problem. The y-intercept you were saying? Yeah, just plug in 0 for all the x's and you'll end up with positive 1. That's it. 0, 1. Right? So plug in a 0 there. There and there, you'll be left with -2 divided by -2, which is positive 1 for the y-intercept. Red box it. So 1 y-intercept, 2 x-intercepts, and a domain. There we have it. Let's move on. Since we know that at x equals 2, the function will be undefined, I will be choosing values to the left and right of 2. So I'll be picking values like 1, 0, -1, and also to the right of 2, I'll be picking 3, 4, and 5. We know that when x equals to 0, the y value is 1, and then we'll plug in these other values to find out the rest of the xy chart here. So for instance, plugging in 1, I'll have -1 in the denominator, because that was easiest. And then you'll have 2 minus 5, which is -3, -3 minus 2 is -5, and you end up with a result of positive 5. That wasn't bad. Plugging in -1, you'll have -3 in the denominator, and in the numerator, you'll have 2 plus 5, it gives us 7. 7 minus 2 is 5. There you go. So this gives us -1 and 2/3. Okay. Plugging in 3, you'll have 2 times 9 is 18. 18 minus 15 gives you 3, and then 3 minus 2 is 1. In the denominator, 3 minus 2 is 1. So therefore, this gives us 1. Plugging in 4, 2 times 16 is 32. 32 minus 20 is going to give us 12, and then 12 minus 2 is 10. And then in the denominator, 4 minus 2 is 2, so 10 divided by 2 is 5. All right. Now plugging in 5, you'll have 2 times 25 is 50. 50 minus 25 is 25. 25 minus 2 is going to give you 23. And then in the denominator, 5 minus 2 is 3. All right. So this gives us a result of 7 and 2/3. Okay. All right, looks like we have stuff to plot now. Let's begin graphing this by graphing our asymptotes first. So remember, we have asymptotes of x equals to 2 as well as y equals 2x minus 1. And so graphing our vertical asymptote at x equals to 2, I'll have a dashed line, vertical line, at x equals to 2. And then I have a y-intercept for the slant asymptote of -1. And I'll be going up 2 and over 1, up 2 and over 1, up 2, over 1. Okay. And then I can go down 2 and over 1. Yeah, I can do that. Okay. Down 2, over 1. See that? And then our dashed line. Okay, just like that for our slant asymptote. All right, that was pretty decent for the slant asymptote right there, right? I did better. All right, and so excited about the fact that I drew that better that time. Thanks. Let's go ahead and plot this stuff. We have a y-intercept at 0, 1. That goes there. Okay, and then let's go with this -1, -1 and 2/3. So -1, -1 and 2/3 is going to be about right there. Okay, and then you have +1 and 5. You can do that. There you go. All right, looking good. And next we'll have 3, 1. 3, 1 is here. Thank you. We have 4, 5. 4 and then 5 is here. Thank you. And then we have 5 and 7 and 2/3. 5, 7 and 2/3 is here. Okay. Well, that's just lovely. Let's go ahead and graph it. So that means that I have a graph that's going to look like this. All right. Arrows on both ends. Thank you. And then I'm going to have this part over here that looks like this. Okay, great. Thank you. There you go. There you go, ladies and gentlemen. And because we clearly don't have any breaks in our range, then that means our range goes from negative infinity to positive infinity. Notice, depending on the graph, you may or may not need a calculator to identify the range of your rational function. All depends. It all depends. Yeah, there you go. It's very interesting. All right, so let's check out our end behavior. The end behavior as x approaches negative infinity, y approaches negative infinity. And as x approaches positive infinity, y approaches positive infinity. There you go. That's what's up. Yeah. So as x approaches negative infinity, this is going to continue to go to negative infinity. As x approaches positive infinity, this top part here, yeah, it's on its way. It's on its way to positive infinity. There you go. Red box it. Red boxing the end behavior. Oh, look at that. Look at that. See, I'm taking care of you. I'm taking care of you. And the range right there. We have, of course, the graph there. Looking good, looking good, looking good. And that completes problem number 4. Yeah. Yeah, that's right. So, ladies and gentlemen, as a reminder, please subscribe to the YouTube channel for Whittington Tutoring. Go ahead and click that like button. Give your dear friend, Mr. Whitt, a like. Thanks. And share the video with people that you know and love. That'll do a lot of help for them. And if you're able, please donate, as that helps us bring you more free math tutorials from me, Mr. Whitt, and Whittington Tutoring. Peace.
Thanks for watching. We appreciate you hanging out with Whittington Tutoring. Like the video, comment, and subscribe. Hit up our website, tutoringmath.net, and set up a private tutorial with me and FBT. Oh yeah, baby.